I did run just shy of time on Monday. I wanted to mention a couple of things before I jump into question and answer. Some things that I think will be helpful with some of the questions that were asked. So, when we think of a definite integral, we're thinking of looking at some function between 2 points. And if we think about the way we do this integral, we start at A and work our way from left to right from A to B. So what would happen if I think of doing this integral? What does switching those numbers mean? So I'm going from right to left instead of from left to right. And if I'm going the other way, my delta x is backwards. So I'm going to get a negative number for all of those widths. And I'm going to get the opposite of the value I got when I did it from left to right. Now, please notice that doesn't mean that this value is negative. This value could end up being positive if this one was negative to begin with. They're just opposite to one another. So not only is the integral from A to B, the definite integral, a signed area, above is positive, below is negative, it's an oriented area as well. We go from left to right. Well, with that in mind, here's an absolute shocker of a claim. I can do this integral even if I don't tell you what function it is. I'm going from here to here. How much area did I cover? There you go. Visually. Let's think about integrating a constant. The integral from A to B of some constant C. Let's draw a picture in our minds. What does the equation y equals c look like? So I chop that horizontal line off at A and B. Resulting shape is a box. A rectangle. Area of a rectangle. But I know the width in this case being the height, is that constant. The length goes from A to B. Since these are pictures in my head of the graph of a function, I'm looking at an area somehow. I can think of making a function into multiple pieces. I can say I want to do the area of this part and the area of the next part, and I want to add or subtract those areas. So if I have two functions that are added, I can think about tearing them apart. Remember, this is really a limit. And back in chapter 2, we had properties of limits that said if I was taking the limit of two things that were added, I could take the limit of the first piece and the limit of the second piece separate from one another. Since an integral is really a limit, I can do the same thing here. It also doesn't matter whether I'm adding or subtracting. So if there was a minus sign here, there'd be a minus sign here. Back when we were first doing derivatives, when we were first doing limits, we said, oh, what if I have a 3 everywhere inside my limit? I can take it out front. The same thing can be done here. I can think of functions as area, right? So if I know that my function is always positive, then what do I know about the integral from a to b of that function? This says that my graph is always above the x-axis, which means all of the y values for my little rectangles are going to be positive numbers. My area is going to give me something positive. Because A is smaller than B in this setup. I can just do it pictorially. If my function is always up, and I'm going this way, then my width is positive, my height is positive for every single rectangle. When you add up a bunch of positive numbers, you get a positive number. Wait a second. Take a look at that picture again. There's actually another thing I can do with this picture. Let me draw another function. If I asked you about the integral from a to b of g of x dx, just based on this picture, what could you tell me with regards to f of x? Oh, wait a second. Everywhere in this picture, g is bigger than f. So if I start adding up rectangles for g, I've got to be adding up heights that are bigger than heights for f. If g is bigger than or equal to f, then the integral for g is bigger than or equal to the integral for f. I could even do that with horizontal lines. If let's say my function f has a minimum value, little m, and a maximum value, capital M, then I know that f is always between those two. Then the integral of f of x has to be less than the integral of capital M. But capital M is a horizontal line because it's a constant. And in the same way, f is always above or equal to little m. So I could integrate little m and get a lower bound. So I can actually deconstruct my integrals. I can take them apart and turn them into pieces. And that means that I could actually do what we did in the example on Monday with x cubed and 6x. I can do the x cubed part separate from the 6x part. And I can separate the, didn't we separate the sums? I did exactly that. I just did it, you justifying it with sums. Now I do it directly with the integral. If I can find an easier way to do these integrals, it's going to make my life a lot easier. because that's the width of my interval. I'm multiplying them. That's the width of my rectangle. One more. Let's consider our picture again. And let's consider some other x value. Now, here's a choice. You can put this x value wherever you want, to the left of A, in between A and B, or to the right of B. Where do you want it? On the left, in the middle, or on the right? Say again? In the middle. So I'm going to put it over here. C. Let's consider drawing that little vertical line. I could do the integral from A to B of f of x. Or I could do two pieces. I could do the integral here from A to C. And I could do the integral from C to B, couldn't I? I can stop along the way. I'm going all the way over here to the left. I'm starting at A, and I'm going to compute my areas, and I'm going to stop here halfway. That's this piece. Then I'm going to pick up and do this piece. It's this integral. Isn't that the same as going all the way from A to B? What happens if I put C to the left of A? Nothing changes. Why? Look at this one. The integral from C to B starts all the way over here on the left and goes to the right. But the integral from A to C is backwards. What happens when I do it backwards? Say again. Somebody muttered under their breath. I subtracted. So isn't that the same as taking the integral from A to B? Subtracting that part off. It's the same answer. And if I put it over here on the right past B, then the integral from B to C is the one that's negative. I don't have to do this with a point in the middle. I can work back or I can work past. Why would I bother to do this sort of? A number of our applications think of integrals as evaluating changes. We'll talk about this more the next couple of days. But sometimes it's useful to have a baseline to start from. If I'm doing time, inflation is the way in which money changes, right? Everybody talks about the rate of inflation. Well, that's the value of money. I need to start with a common year. So I say, oh, inflation since when? And I use that information. These ideas will help us deal with the problems we are looking at, not just in these two sections, but moving on further. Apologize for not getting to this on Monday. But what questions do you have? The same equation as this one. Because this part is negative and this part is bigger, so negative to match this up. Again, let me wait until section 5 and section 4, and I'll show you a baseline problem. It'll hit. The whole point is that it works regardless. If it helps, let's rearrange the equation. Maybe it looks better if I write it like this. The integral from C to B is the integral from C to A plus the integral from A to B. But notice, I can put that on the other side. That'll make it negative. But so it'll go from A to C and C to B when I flip the limit. So with that done, questions 5-1, 5-2. Yes, ma'am. It's your call. You can use a left, you can use a right, you can use the middle. It's completely up to you. But my goal is for you to tell me A, how many rectangles you're going to use, and B, what the height is for each one. But because you've got this picture, you can decide completely on your own. And yes, just estimate the Y values off the picture. Like 22. Okay, you want to do 21 or 23? Okay, in 21, we are given limit as n goes to infinity, sum I equals 1 to n, 2 over n times 1 over 1 plus 2i over n. Ew. And we're asked to turn this into an integral, right? Okay, hang on a second. I need to remind myself of the statement in the definition that says the integral from a to b of f of x dx is the limit as n goes to infinity of the sum I equals 1 to n f of xi star delta x. So somewhere in this stuff, I have a delta x and I have an f of xi star. And those two pieces are multiplied together, right? So I start looking up here. And I see a piece that's got i's in it. I'm pretty sure that's going to go with my f of xi star. And then I've got this other piece. I'm going to run with that being my delta x idea, because it's not going to change as I changes, right? Okay. Now let's go back to the calculations that we did when we were thinking about how to set up a Riemann sum. Here's my x-axis, all chopped up into little bits. If I want to use this to come up with delta x goes from the left end to the right end. I subtract right minus left, and I divide by n. That's the piece I think is delta x, right? So I think 2 over n is b minus a over n. Well, if that's true, then b minus a is 2. Now that means I have some choices, because I don't know what a is. I just know that b is 2 units bigger. Okay. Let's look at the other part now for a second. When I was making these little subintervals, I started over there at A, that was x0, the next one was x1 and x2 and so on, right? So what is the x value here? What's x1? It's A plus one step, right? Okay, wait a second here. That should be the thing I use. Either I use x0 or x1 in my first interval. I'm either doing a left or a right, maybe a midpoint. I should look at what's in the xi star bit and see if I can match this up now. If I used the left edge when I is 1, then I would have 1 and no steps. But that's not true, because if I put 1 in up here, I get 2 over n, don't I? Isn't that what I get right here? So x1 looks like it's what happens here when I do 1. If that's the case, I'm doing a right end sum, aren't I? All of a sudden, I recognize that thing as x1 star. Wait a minute. That is equal to 1 plus 2i over n when I is 1. What's A? And if A is 1, what's B? Now, that means that that thing on the bottom of that box right here, that's xi star. If that's f of xi star, what's f of x? Say that again. 1 over x. Hey, wait a minute. I want to write an integral, yes? To write an integral, I need to know a and b and f of x. And we now know a and b and f of x. All I have to do is translate from one geek speak idea to the other geek speak idea. I'm just looking at the way to write this. That's true. Because there's another way I could write this. This is not unique. What if I decided that I was going to set this up a little differently? And I said up here, hey, I've got b minus a is 2. I'm going to decide right now that a is 0 and b is 2. Right? I can make that decision right there. Then I go back and I start saying to myself, I've got this number line, right? What's the x value right here? And that's what I get when I put in 1, right? Because this is x0, this is x1. So I should use I equals 1. Yes? I go back and I look at my thing and I say, oh, 1 over 1 plus 2 over n should be f of x star. Right? Then what's f of x? Then f of x is not 1 over x, it's 1 over 1 plus x. The 1 plus is not part of a xi, it's extra. I think of the plug-in as happening right here, as opposed to the whole thing like that. So I get a different answer. I get the integral from 0 to 2 of 1 over 1 plus x dx, which is going to give me the exact same result because it's the same picture shifted 1 unit to the left. Well, it does ask me to write an integral, so yes, I want to write the integral. Well, then I could draw a picture if you really wanted. But what I have in the first version, the integral from 1 to 3 of 1 over x looks like this. But when I draw this picture, I'm asking for the exact same region. I just picked it up, moved it over. Ideally, I want an explanation. You can do this all in words. How much work? As much as you're willing to give me. Show me what you were thinking. Oh, well, then if you just came to you in a dream, then the dream gets the points and you don't. But do you see how there's multiple ways to get the same answer? It depends on what I decide the function is. Once I know what xi star is, once I know what delta x is. Yes.
Is there any, like, is there any better than 14 around?
Is there any better what? Oh, we could look at 13, which is very similar. Right? So 13 says our car is decelerating. We're applying the brakes. Figure out how far it went. Now, in this particular graph, the y-axis is labeled in feet per second. The x-axis is labeled in seconds. So what I really need to figure out the area, feet per second times seconds, gives me feet, right? So if I took a height, I could make rectangles at different points on this graph. I am going from 0 seconds to 6 seconds. Might as well use 6 rectangles, 1 for every set of blocks I've got. Do you want to do a left sum, a right sum, or a middle sum? A right sum. So I go to the right end at each second. At 1 second, I get this point. At 2 seconds, I get this point. 3, I get this point. 4, 5, 6. Now I need to estimate. What height is that? Okay, we use 50. What height is this? Okay, 33. This one? 22, 18, 8, 0. But now I can say, I'm building my rectangles. This rectangle had a height of 50. Well, it looks a little lower than that to me, but you called it 50, and a width of 1. What's the area of that rectangle? 50. Plus, you said 35 times 1. I'm at 50 and 35 is 85. 22, right? 85 and 22 is 107. 17 times 1. 107 and 17 is 124. You said 8 for this one. Gives me 132. And the height of the rectangle here is 0. I come up with 132 feet using your numbers. There you go. Feet per seconds times seconds gives me feet. No problem. In 14, there's a problem. What's the problem in 14? The y-axis is in kilometers an hour, and the bottom is in seconds. I've got to convert one of these to something else. I could go kilometers per hour to meters per second. I could go seconds to meters. Can't go seconds to meters. I go seconds to hours. I got to convert one of the units to make them cancel. You're looking at me like I've done something bad, Gracie. It's an estimate, right? I'm doing a Riemann sum to estimate. Because really what I want to do is I want to get the area under that graph. Pick one. You could do right and left and average them. You could do a midpoint. There are lots of other ways to approximate this area. I just want an easy one. By the way, you could use more rectangles. You could use fewer rectangles. It's your call. 34 and 5.2. So now we're actually asking you to do the whole thing the hard way. Yep. So this is the same thing I did in class. Take a look at 30. 30 is the integral of 6 minus x squared from 0 to 4. So this time I'm going to do the reverse of what I did for Angela's problem. Instead of figuring out what it is from the sum and writing it as an integral, we take the integral and write it as a sum. If I am using n rectangles, then delta x, the width, should be 4 minus 0 over n, or just 4 over n. Now, the problem in question, the statement in theorem 4, tells me to use a particular xi. So I even know which xi I'm going to use. I'm going to use 0 plus I times 4 over n, which is just 4i over n. I don't have to keep adding 0. So let's write this as a sum. Limit as n goes to infinity. Sum I equals 1 to n. F of xi star. 6 minus this thing squared. Times delta x. Everything for the next 5 or 6 lines is just algebra. I need to square the thing that's squared. I need to take the 4 over n on the outside of the parentheses, put it into the parentheses. Square a fraction means you square the top, you square the bottom. 4 squared is 16, n squared and I squared. Now I multiply in the 4 over n. And I get 24 over n minus 16 times 4 is 64. I squared over n cubed. Okay. Now, I split this into 2 separate sums. The 24 over n, separate from the 64 I cubed n cubed. Now, anything that's not an I can be taken from inside the sigma to in front of the sigma for each sigma separately. "24 is not an I, put it out front. N's not an I, put it out front." What did I leave behind? But I took stuff out, so I have to leave something behind. When you factor, you leave a 1. 64 is not an I, n cubed is not an I. I'm going to take the limit of this whole thing later. So I need to make sure I remember that that limit is out there. Now, I need the page on which theorem 4 is written. Page 387. And at the bottom of that page, I have 4 pieces of summations. Please look at line number 5 and line number 7. Because line number 5 tells me to do what I do when I add up a bunch of 1s. And line number 7 tells me what I get when I add up a bunch of I squares. And isn't that exactly what I'm adding up here? So I know this sum can just be replaced by the letter n. And this can be replaced by that expression n times n plus 1 times 2n plus 1 all over 6. Without those formulas on page 387, I'd be completely screwed here. So I'm very glad we have them. Because now I simplify what I can. What happens with that 24 and the n and the n? Which just leaves me 24. This one, on the other hand, is a little more disgusting. So I look at this and I say, wait a minute. I'm multiplying on the bottom there. I'm multiplying n cubed by 6. Do you care what order you multiply things in? So let's switch the order. Let's put the n cubed on the right and the 6 on the left. So I get 64 over 6. And then on the bottom here, I get an n cubed. But I look at the top for a minute. And I start thinking to myself, what's that going to be if I multiply it out? Careful. There's a 2 there. So if I actually multiply this out, I'm going to get a 2n cubed. Because when I multiply this part out, I get 2n squared plus 3n plus 1. Then I multiply in another n, I get 2n cubed plus 3n squared plus n. So it isn't just a 1n cubed, it's a 2n cubed. Why do I care? Say again? Almost. I don't just cancel. When I take the limit, the highest power and the lowest power, highest power on top and the highest power on the bottom match. So the limit gives me the coefficient. I'm going to get a 2 when I do that limit. So when I take the limit as n goes to infinity, I get 24 minus 64 over 6 times 2. Which makes my life a lot easier. Because that's a number. I found the area. I'm done. What is this number? I don't know. This is going to give me 64 over 3. 24 multiplied by 3 over 3, I get 72 over 3. So I get 8 over 3. This is the long, ugly way to do this. Hell no. Do not memorize these things. No. Put a post-it note in the book. Put a star, a bookmark on your PDF file. I don't want you to memorize this crap. Now, I will give you another wonderful piece of information. This represents an area, right? It's the area under that curve between 0 and 4. There's my picture. Notice that there's a lot of negative stuff between 0 and 4 because we cross between 2 and 3. I wanted to move the picture up a little. When I get to 4, I'm down there at negative 10. So really, I have a bunch of negative area and I have a bunch of positive area. If you made this picture on a piece of paper, you could shade the area we wanted, right? Above trace, it says calculate. Yes. Hit second trace. Do you see something useful? Option number 7 looks like an integral. So I hit number 7. And what does it ask me for? What is my lower limit of integration? That's A. 0. It asks me for an upper limit. That's B. 4. Eight divided by 3 is 2.666, repeating, isn't it? I got it right. it even shaded the damn thing in for me. Good technology, thank you. Do you know how it did this? It did a Riemann sum with delta x being 10 to the negative 12th. That's a really fast computer, isn't it?
How do you think it's going about solving what's in 42, 46? Is it?
It actually tells me to do it with geometry, doesn't it? 42 and 46? So you draw me a picture. Chloe, was that the one you were going to ask about as well, or do you have something else? Okay, I'll get to you in just a second. So let's look at 41. 41 is the integral from -2 to 5. Of 10 minus 5x. Wait a minute. 10 minus 5x is a line. Goes there at 10. It's going to go through the x-axis at 2. So somewhere out here is 5. I'm going to -2. How do you find the area that we would shade in? Oh, there's a triangle here and a triangle here. You can find the area of a triangle, can't you? Do I need to do any calculus at all? Hell no. Now in 45, I have the integral from -3 to 0 of 1 plus the square root 9 minus x squared. Well, that's disgusting. But let's break it into two pieces. What's the graph y equals 1? A horizontal line. This area is a rectangle. What's the graph y equals the square root of 9 minus x squared look like? Hang on a second. If I square that, I get y squared equals 9 minus x squared. If I move that over, I get x squared plus y squared equals 9. What shape is that? That's a circle. It's not just any circle either. It's a circle whose center is 0 and whose radius is 3. Which means this is the upper half of that circle from -3 to 3. Oh, wait, I only want to go to 0, so ignore this part. What's the area of a quarter circle? I'm done. No calculus required. Crap ton of algebra required, but no calculus. Geometry. Integrals are areas, but they're more than that. Before tomorrow afternoon, go listen to Eminem without me, because I'm going to bring to you the best theorem in calculus tomorrow. I'll see you all then. A wonderful rest of your day. If I have your exam, you should come get it.